Hi everyone. I'm going to talk about double balance sets in high dimensional expanders. I'm David Maas, and it's a joint work with Tali Kaufman. So let's start with the objects we study. A d-dimensional simplicial complex X is basically a d+1 hypergraph with a property that is closed under taking subsets. Let's see an example. Of a three-dimensional simplicial complex. So its three-dimensional simplicial complex is a 4 hypergraph, meaning each face is of size 4. So it has pyramids, basically. In this example, the pyramids are 1, 2, 3, and 4. So it's this pyramid and also this pyramid, 3, 4, 5, and 6. So it's a very small example. It has two pyramids. And it's closed under taking subsets, meaning each subset of each of these pyramids is also a face in the complex. So it has this set of triangles, all the triangles that are contained in these pyramids, 1, 2, 3, 1, 2, 4, etc. It has also all the edges that we can see in this example, and also all the vertices. Right, so that's a simplicial complex. That's a very simple, small example. And let's move on to see the common definition of what pseudo-random sets are in a simplicial complex. So I'll start with what is a localization of a set. So what's the localization of a set? We think of a set A of k faces and a face sigma of some dimension L. The localization of A to the face sigma is the set of faces in A that contain sigma. Let's see in this example. So for instance, if A is the set of these three triangles, these three green triangles, and we want to think of the localization of A to the vertex number 1, this vertex. So it's just the triangles in A that contain this vertex. It's just this triangle 1, 2, 3. So out of these three triangles, this triangle contains the vertex 1. So that's the localization of a set A to, in this case, a vertex. And what does it mean that the set is epsilon pseudo-random? So it's epsilon pseudo-random in dimension L if for every sigma, which is a L dimensional face, the fraction of if we look at the localization of A to the face sigma, out of all the faces that are contained, that contain sigma, it's at most epsilon. So in words, it means that A is sparse in every local view. So for example, in this example, if we look at the localization of A to the vertex 1, the fraction of faces in the localization of A to the vertex 1 is 1 out of 3 possible triangles that contain this vertex 1, so it's third. So that's just an example. We say that a set is pseudo-random if it's sparse on every localization. If we want to think of it intuitively, it means that the set it looks like a random set, so it's spread out on, it's not concentrated on one small area, because it has to be sparse on all the faces. Right, so that means that a set is pseudo-random. That's the common definition of a pseudo-random set. So why pseudo-random sets are important? Why do we care about pseudo-random sets? The main motivation is of previous works that pseudo-random sets basically satisfy a sort of small set expansion. So if we look at pseudo-random sets, small pseudo-random sets, they expand very, very good. And the main methods that previous works used is basically sort of Fourier analysis methods. And the limitation is that it works only in direct product spaces, or something which is approximate direct product spaces, where basically each function has an orthogonal decomposition. So if we can decompose each function, it has an orthogonal decomposition, we can apply Fourier analysis methods, and then we can prove small set expansion for small pseudo-random sets. And that works in complexes like the complete complex or two-sided local spectral expander. I don't get into the definitions, but it works in some sort of complexes. So that's basically what previous works studied, and our motivation is coming from the fact that known constructions of high-dimensional expanders, for instance, the famous Riemann-Engel complexes, they are only one-sided local spectral expanders, or in other words, they do not have an orthogonal decomposition. So if we look at complexes that we know that appear in nature, in a sense, they don't have this orthogonal decomposition, and hence we can't use previous methods to show small set expansion in these sets. And our question is there some similar pseudo-random property that we can study that implies small set expansions in, let's say, Riemann-Engel complexes or complexes that do not have an orthogonal decomposition? So that's our question, and for that we define some sort of other pseudo-random property, and let's get into it now. So we call it double balanced sets, but for that I want to show another way of localization. So we want to combine two perspectives of localizations. I'll remind the localizations that we discussed before. A localization of a set A of k faces to an L phase sigma is all the, as we said, is all the faces in A that contain sigma. So in this example we saw before, we have, if we have the set A containing these green triangles, then the localization of A to the vertex 1 is just this triangle that contains the vertex 1. And we can think of another perspective of localization, which is this definition of what's called restriction of a set to an L phase sigma. That's all the faces in A that together with sigma form a k plus L phase. So again, in this example, if we look at the restriction of A to the vertex 1, that's this triangle, which now it's not containing the vertex 1, but together with the vertex 1, it forms a pyramid. So we can think of these two perspectives of localizations. One is what's called localization. That's all the faces that contain a certain face, and a restriction is all the faces that together with that face compose larger face. So okay, that's two perspectives of localizations, and we define what we call double balanced sets. So we say that a set of k faces is alpha double balanced in dimension L if for every face sigma of dimension L we have this inequality. So again, we look at the fraction of faces in A in the localization of A to the face sigma, but we want it to be bounded by this quantity. So let's think of it. So first, the left-hand side is that's what I said, the fraction of k faces in the localization of A to sigma, and this thing. So let's fix vertex v. So it's an average over vertices v and sigma. But let's think of a single vertex v in sigma. Then what is this expression? We look at the localization of A to sigma minus v. So it's basically the faces in A that contain all vertices in sigma except this vertex v, and then we restrict it to the vertex v. So it's basically the average over vertices v in sigma of the fraction of k faces in the restriction to v, that's the restriction of v of the localization of A to sigma minus v. So it's a bit complicated to get it like that, so let's see an example. Again, we have this example. We have the set A of these three green triangles, and let's think of sigma. It's this red edge, 1, 3. Now the left-hand side is what we discussed before. It's the localization to this edge. So it's the localization of A to this edge 1, 3. It's only this triangle 1, 2, 3. So only this triangle in A is contains this edge 1, 3. And there are possible two triangles that contain this edge, so it's half, right? So the left hand side in this example is half, and the right hand side, so let's see it slowly, we have the average over vertices in this edge, so we take the average of over vertices 1 and 3 of this expression, so we look at the localization of A to this edge minus a vertex, and then restrict it to this vertex. So how does that look? So the average, so we have half. So for V equals, let's say 1, we look at the localization of A to the vertex 3, and then restrict it to the vertex 1, and here it's the opposite. We localize it to the vertex 1 and restrict it to the vertex 3. So what is this one? The localization of A to the vertex 3. Basically, it's all the triangles in A, right? Because all triangles here contain the vertex 3, but only this triangle 2, 3, 4 is in the restriction to the vertex 1. So basically, so the localization of A to the vertex 3 is all these green triangles, but only 2, 3, 4 is a triangle that together with 1 forms a pyramid. So this expression here is basically this triangle 2, 3, 4, and when we look at this one, so the localization of A to the vertex 1 is only this triangle 1, 2, 3, but it doesn't form a pyramid with the vertex 3 because it contains it. So this is basically an empty set, and if we sum it, we get here again half. So yeah, it's a very simple small example, but the idea is that we somehow combine these two perspectives. That's some pseudorandom property that we defined, and we want to get something from it. So what are the advantages of this definition of what we call double balance sets? So what I want to claim is that the combination of these both localizations, it gives new insights that apply also to known constructions of high-dimensional expanders, for instance, Rho-Nugent complexes. And the fact that I'm going to use is that when we look at a one-sided local spectral expander, the restriction of a set to the vertices is sparse on almost all the vertices. So if we look at the restriction of a set to the vertices, we get something which is sparse on all the vertices, meaning that for almost every vertex V, we have this inequality. The restriction of the set to the vertex V is basically something like what we expect. Is bounded by the fraction, the total fraction of the set A. So let's just, for example, show that actually double balance sets imply something which is, it's not pseudorandom, but almost pseudorandom, meaning that if a set A is, if it's small enough and double balanced, then we can show that almost all the L faces satisfy this pseudorandomness property. And if we want it more formally, if we look at a one-sided local spectral expander X, and we look at a set A, which is alpha double balanced, and okay, this small, yeah, it's small enough, then the probability if we pick a face sigma of dimension L, what's the probability that it satisfies this pseudorandomness property, right? This was the common pseudorandomness definition, that we want the fraction of faces in the localization to be in A to be at most epsilon, and okay, so the probability that it satisfies this property is very close to 1. So we can show that if a set is double balanced, then it's almost pseudorandom. It's not exactly pseudorandom because it doesn't hold for every face, but if it's small and double balanced, it's almost pseudorandom. And let's give very briefly the idea of how to prove this, and we can maybe understand from it how we use this combination of perspectives. So let's think of a vertex. For almost every vertex V, we have, okay, so let's think of each inequality by one by one. So if we look at the localization of A to the vertex V, that's what we are interested in for the pseudo-randomness property, then because A is double balanced, it's bounded by the alpha times the restriction of A to the vertex V, and then by the fact that X is a high-dimensional expander, as I mentioned the fact before, the restriction is bounded somehow by the total fraction of the set A. So the localization of A to a vertex V by the double balanced property, it's bounded by the restriction to V, and that is bounded by the total fraction of A. So if A is small enough, then it's actually sparse on almost every vertex. So that's pretty simple, but now let's see that it's get a bit more complicated when we look at edges. So if we want to show that it's also sparse on the edges, so for almost every edge, now we have a bit more complicated inequality, but let's move it step by step. We look at the localization of A to some edge UV. That's what we are interested in. And then by the double balance property, we know that it's bounded by alpha times, okay, so it's an average, so it's alpha over 2, the localization of A to the vertex U, and then restricted to V, plus the localization to V and restricted to U. And okay, so that's by the double balance property. Then we use the fact that a restriction of a set is sparse almost everywhere. So we move because X is a high dimension expander. So we know that the restriction of this localization, the restriction to V, is bounded by just this amount, this fraction. Also, the restriction to U is bounded by this fraction. And then again, we can use the fact that A is double balanced and know that this localization of A to the vertex U is bounded by alpha times the restriction to U, and again, similarly by for V. And then we can use the fact that X is a high dimension expander, and we know that each restriction behaves nicely, and we get something like that. So again, we get that for almost every edge, the localization of A to this edge is bounded by this total fraction of A, okay, times alpha squared. And if A is small enough, then it means that it's sparse on almost every edge. So the idea is, you can see here, we move step by step. We use the double balance property, and then the expansion property, and then again the double balance property, and then again the expansion property. And if we look at a face which is a higher dimensional face, then we have more steps. But the idea is that if A is small enough, then it's also almost pseudo-random. That's the idea. We use this combination of two perspectives. Okay, so that's we have this, that being double balanced is sort of a pseudo-random property. It implies almost pseudo-randomness. Let me just mention some applications that we got from it. So first we get, as I started, we are interested in small set expansion for pseudo-random sets. So we get something which is optimal delta 1 expansion. So what is delta 1 expansion? I'll just mention the delta 1 expansion. There's the delta 1 of a set A is the set of k plus 1 faces that contain exactly one face in A. So if A, let's say, is a set of triangles, delta 1 of A is the set of pyramids that contain exactly one triangle from A. Okay, so that's basically it measures somehow the expansion of the set. And what we show that if A is alpha double balanced and very small, so it has to be smaller than epsilon over k plus 1 squared alpha to the k. So if it's that small, then the fraction of delta 1 of A is bounded by k plus 2, the fraction of A. So the k plus 2 basically is the optimal thing we can hope for, because let's say each pyramid contains 4 triangles. So okay, you can calculate it, but the optimal thing we could hope for, that delta 1 of A would be k plus 2 over this fraction of A, we get almost optimal, so it's 1 minus epsilon this quantity. So for sufficiently small sets, we get very strong expansion. And also, if we look at some larger sets, let's say set of size, so here it has to be smaller than epsilon over alpha to the k. Here it's close to 1 over k plus 1 alpha to the k. So if it's small but larger than before, then we have some delta 1 expansion, meaning the delta 1 of A is larger than 0. So we have some delta 1 expansion for small sets, but larger than before. And why is this important? So it's tightly related to size of cohomologies. So I don't have the time to get into the definition of cohomologies in complexes, but I'll just mention how we use it for getting some bound on the size of cohomologies. So what we show basically is that cohomologies are double balanced, meaning if we look at a complex X with some, okay, so it has some expansion property for its links. Basically, Riemann-Roentgen complexes satisfy this property. Their links are beta coboundary expanders. Then every cohomology element A is alpha double balanced for alpha which equals something which is related to this expansion in the links. So cohomologies in certain complexes are double balanced, and what we get from it, that they must be large. So if we look at these complexes which have this beta coboundary expansion property in the links, then every cohomology element must satisfy this inequality. It must be at least this large, because otherwise the cohomology element, by definition, it has no delta 1 expansion. It has delta 1 equals 0. That's by definition of a cohomology element. So if it would be smaller than this quantity, by our theorem from before, it would have some delta 1 expansion, contradicting the fact that it's a cohomology element. So every cohomology element must be at least this large, and just to get some context, it's exponentially better than was known before, because previously it was only known that every cohomology element in these complexes are at least this large. So we have here 2 to the k, and are bound by combining these two localization perspectives is exponentially better. So it's much larger than it was known before. And let me just summarize. I mentioned that previous works studied pseudorandom sets, but only in spaces that have an orthogonal decomposition, and hence they could use Fourier analysis methods. If we want to apply it in other spaces like Riemann-Roentgen complexes, we can't use previous methods. So we looked at another perspective. We look at the combination of two localizations perspectives, and what we got, it implied a new method for studying pseudorandom sets on other spaces like Riemann-Roentgen complexes. And some applications that we got from it is what we call delta 1 expansion, or in other words, small set expansion for double balanced sets. And also we got an exponential improvement over the state-of-the-art size of cohomologies. And it's interesting to ask if this combination of perspectives could lead to more insights, because there are many works that studied localizations, and there are other works that studied restrictions of sets. And what we suggest is maybe to look at these perspectives combined together and maybe get more insights that we couldn't get before, maybe improve other results that were known before by this combination. And what we show that actually for this specific application for size of cohomologies, we actually get an exponential improvement over what was known before. So maybe this combination of perspectives could be useful in other works as well. Yeah, so that's basically it, and thank you.